So recall the small signal circuit method had three steps. As the first step, you were supposed to go and find the operating point of the circuit by picking values for a DC bias for ID, VD, and so on. As a second step, you replaced all the elements in your circuit with their linearized models for each element. So linearized models for each element. So you got linearized models for each element based on the DC operating point values. In this section, we are going to focus on how to obtain linearized models for several example elements. And then finally, as a third step, you went and analyzed a resulting linear circuit. Okay? So here we will focus on step two, which is how do you find linearized models for each of the elements in your circuit? Okay, and beyond that, the rest of the method is simple. You pick operating point values and you do a nonlinear analysis to find the output. You pick linearized models, and then you analyze a resulting small signal linear circuit. So here, let's go and find linearized models for several elements that we are familiar with. So let me start with a DC supply with a voltage, fixed voltage V0. Okay, how do we find a linear small signal equivalent for this DC supply? So let's start with a large signal model for this. So the large signal model for this is the device, the element itself, where I simply replace capital I, capital S, and capital V, capital S, and where Vs equals V naught. So that's the straightforward large signal model for my voltage source. So for the small signal model, we'll first do it intuitively, and then we'll do it using the analytical approach that I showed you earlier. So intuitively, what do you think? So we need to find a resistive equivalent for this voltage source, and we're trying to find out the following. We're trying to say for a small signal change. Okay, so supposing I have a current here, for a small delta change in the current, okay, for a small delta change in the current, by how much would my voltage change? Okay, that's the element I need. Okay, so for a small change in the current, by what does the output voltage Vs across the voltage source change? And the answer is, as I change my current by some delta, there is zero change in the output. Okay, in the voltage across the element. So this indicates that I can replace a voltage source with a short circuit where Is is the small signal current and Vs is the small signal voltage across the element. So notice here that if I change my input current Is, my small signal current slightly, then for a short circuit, Vs does not change. Vs is the same. And so this is my small signal model for my voltage source. Now I can also derive this analytically using the method I described earlier. And so I can write small signal Vs. I can go ahead and for the voltage source, recall that the equation for the voltage source was Vs equals V naught. So I can use that equation. So this was the f of ID, Vs equals f of ID equation for the element. Now notice that whether it's Vs equals a function of ID or whether it's ID a function of Vs, it doesn't matter. For different elements, you can pick whichever you want. It's completely symmetric. So for Vs, I have to go and differentiate the function and then pick the operating point value and then multiply by the increment. So here's what I get. So I get del V0 by del Is, and I evaluate that at Is equals the DC value I capital S times small is. Okay, so notice that